Okay, so in this video, I will be finalizing the last part of topic 4 in electrochemistry for chemistry 0620 Cambridge IGCSE. This is part 2, completing from the extraction of aluminum. Okay, so let's begin. Extraction of iron from its ore. So in the previous video, we discussed what was iron. What was an ore? Ore is the natural mineral from which you can extract a metal, correct? And we learned that the main ore of aluminum is bauxite. Okay, we use bauxite, we extract aluminum by electrolysis. Okay, and we use another ore in the process, which is cryolite, to reduce the melting point of aluminum, and etc. and so forth and so more. Now we will have a look at extraction of iron from its ore. What is the main ore of iron? The main ore of iron is hematite. Hematite is the main ore of iron that contains Fe2O3 iron oxide. Okay, it contains more than 60% iron. Now, what is the process? Is it this by electrolysis? Nope. We do not extract iron from its ore using electrolysis. We do it using a blast furnace by reduction with carbon. So this might sound something new. I know the page looks quite complicated, but do not worry about that. I will explain it. So a blast furnace is a furnace for extracting metals by reduction with carbon using hot air blown at the base to raise the temperature. I know the definition is quite big, but give me some time to explain it and just stick with me, okay? So aluminum was extracting using electrolysis, and we know what is electrolysis, correct? Breakdown of ionic compound using electricity. Iron will be extracted using a blast furnace. A blast furnace is a furnace, okay? Actually, let me open the diagram for it to be better. This is a blast furnace, okay? This is a blast furnace, okay? And according to the definition, it is a furnace for extracting what? Metals by reduction with carbon using hot air blown at the base to raise the temperature. So, we use this furnace to extract a metal using reduction. Reduction is gain of electrons in the reactant side with carbon. How do we do that? By blowing hot oxygen air at the base of the blast furnace. Again, blast furnace is a furnace used for extracting metals with reduction of carbon by blowing hot oxygen at the base of the furnace to raise the temperature of the furnace. Okay, that is the definition of the blast furnace. If you have understood this definition, everything will be easy. Now, in this process of extracting iron, we have some raw materials. The raw materials that we need to add in the blast furnace in the beginning of the process is hematite, which is the main ore of iron, limestone, which is calcium carbonate, and excess graphite, also known as impure form of carbon. These are all added on the top of the blast furnace, okay? So on the blast furnace, we're going to add these raw materials, as you can see here, on the top of the blast furnace, okay? From here, step 2. Now, we blow the hot oxygen at the base, okay? We blow hot oxygen at the base of the blast furnace. Why do we do this? To burn the carbon and form carbon dioxide. There's carbon present. In the beginning, we added an impure form of carbon. Now we blow oxygen. This blown oxygen will react with the carbon and it will form carbon dioxide. This reaction is an exothermic reaction, releasing heat in the product side. Hence, it will increase the temperature of the surroundings. The surroundings is the furnace. It will increase the temperature of the furnace, raising and heating it up, okay? After this, again, the equation the excess carbon we added in the beginning will react to the blown in oxygen, forming carbon dioxide, releasing heat to the blast furnace, increasing the temperature as an exothermic thermal chemical reaction. Now, the unreacted excess carbon graphite. What does this mean? We formed carbon dioxide. Some carbon did not come in the carbon dioxide. Some carbon was remaining, okay? This remaining carbon will react with this formed carbon dioxide. So this formed carbon dioxide will remain with the excess carbon that was remaining in this reaction, and it will form carbon monoxide. Okay, carbon monoxide. So in this reaction, carbon dioxide is reduced to carbon monoxide. According to the definition of reduction, one of the signs of reduction that we have studied in the first sheet of topic 4 electrochemistry regarding the redox reactions is that reduction is when oxygen is reduced or decreased. So in step 3, the unreacted carbon will react with the formed carbon dioxide and it will be reduced to carbon monoxide. Now, carbon monoxide is a very strong reducing agent. What does this mean? What is a reducing agent? A reducing agent can take oxygen. It can oxidize substances. So, reducing agent can take oxygen from any compound. Well, not reducing agent, I mean carbon dioxide, which is a strong reducing agent that can take oxygen from any compound, okay? So, this carbon monoxide that has already been formed will reduce hematite, which is the main ore of iron that we added in the beginning. If you remember, we added hematite, limestone, and carbon. Till now, we have only been dealing with the carbon and oxygen. Now let's deal with the hematite. This carbon monoxide that has been formed will reduce the hematite, meaning that it will it will act as a reducing agent, and it will form molten iron at the bottom of the furnace. So iron oxide will react with this carbon monoxide and it will reduce it to iron and carbon oxide. Now limestone is added. So basically limestone was there, we did add it in the beginning with the other substances, okay? But now that carbon monoxide has reduced iron oxide, there is molten iron at the bottom of the furnace. So now we will add limestone, which is calcium carbonate. Why? This will remove the impurities in the molten iron at the bottom of the furnace. These impurities include SiO2, sand. So calcium carbonate will thermally decompose into calcium carbonate and carbon dioxide. Thermally decomposes to form calcium oxide and carbon dioxide, okay? Sorry, this should not be here. Yep. Yeah, so calcium carbonate will thermally decompose into calcium oxide and carbon dioxide. Why? To remove the impurities. After that, what has happened? The calcium oxide reacted and thermally decomposed into calcium oxide and carbon dioxide. This calcium oxide that is formed will now react with silicon dioxide, an impurity in the iron ore, and it will form calcium silicate, calcium Ca, silicon Si, oxygen silicate, CaSiO3, which is also known as molten slag. We will learn more about this in the next page. So calcium oxide reacts with silicon oxide to form calcium silicate. I'm not going to stop there. I'm going to repeat the process in a brief summary, okay? So, extraction of iron from its ore. The main ore of iron is hematite. Hematite includes Fe2O3, more than 60% of this ore. The process begins by us adding raw materials into a blast furnace. Okay, we add hematite, the main ore, limestone, and excess graphite. What happens first? First, we will blow hot oxygen at the bottom of the blast furnace. This hot oxygen will react with the carbon that we added, forming carbon dioxide. Okay, this reaction is a exothermic reaction. It will produce heat and increase the temperature of the blast furnace. From here then, the carbon that has been remaining from the carbon dioxide reaction will react with the carbon dioxide that has already been formed. It will form carbon monoxide, okay? And now this carbon monoxide that has been formed, how was it formed? It was reduced, okay? Why? Because the number of oxygen was decreased. Now, a note, carbon monoxide is a strong reducing agent, meaning it can take oxygen from any substance. So carbon monoxide will reduce the main ore, which is hematite. It will take the oxygen from hematite and it will form molten iron at the bottom of the blast furnace. The equation will be Fe2O3 will react with 3CO, carbon monoxide, to form 2Fe plus CO. Again, please do refer to the state of matter of each of these elements and compounds because each one counts as a mark. Now, limestone that we added, we will add some limestone to remove the molten impurities. We know that carbon monoxide reduced the iron hematite at the bottom of the blast furnace. Now we will add limestone, calcium carbonate. This will reduce or remove the impurities, which is SiO2 sand. Okay, so limestone, calcium carbonate will thermally decompose into calcium oxide and carbon dioxide. This calcium oxide will forward react with silicon dioxide, which is one of the main impurities, and it will form calcium silicate, CaSiO3. CaSiO3 is also known as molten slag. The equation for this is going to be calcium oxide plus silicon oxide will give CaSiO3. This is the diagram for this extraction using the blast furnace. Okay, now I'm just going to go through some quick facts about molten slag. Molten slag is much lighter than molten iron, so it will float on the molten iron. Okay, after reducing SiO2 forming molten iron, a new iron is formed. This is known as cast iron. Cast iron is a very hard and strong iron. It cannot reshape. These are properties of not a metal and alloy. Alloy is not a pure metal. Cast iron is not a pure metal. Cast iron is an alloy. Alloy is a mixture of two or more metals that makes metal harder. The structure of alloy as it is provided here: small particle and then big particles in between to prevent sliding. Okay, how do we convert this cast iron into mild steel? We do this by reducing the impurities in cast iron. The main impurities in cast iron include carbon, sulfur, silicon, and phosphorus. So to reduce these, we will apply two experiments. The first one, we will add sulfur and carbon to form SO2 and CO2. These will escape as gas, so the impurities are gone. To remove the furthermore impurities, phosphorus and silicon will form molten oxide, and it will be removed as slag after adding calcium oxide to the blast furnace. Okay? Rusting and its preventions. What is rusting? Rusting is a corrosion chemical reaction between iron, water vapor, and oxygen, Fe, H2O, and O2, to form a compound. What is this compound? Hydrated iron oxide. Hydrated iron oxide is known as rust, a red brownish powder. In the previous sheet, we learned why rust is formed and how it is formed compared to aluminum. Now we will learn some barrier methods to prevent rusting. The first two are very simple: painting and oiling and greasing. Both of these will prevent any contact between oxygen and iron to prevent any rust reaction. Now, a key point to consider here. Rusting is oxidation, and reduction occurs at the cathode. So, if there is no oxidation, there is no rusting, correct? This is where cathodic protection comes in. If we connect this steel to a cathode, it will prevent rust. Why? Because there will be no oxidation and there will be no rusting. Sacrificial protection, attaching plates of a more active metal to a less active reactive one. So the more reactive metal will oxidize and corrode first. It will protect the less active iron from reacting with oxygen and preventing rust. The last one is my personal favorite, galvanizing, which is something we see very often. Galvanizing is basically the complete coating of iron by zinc. Why do we use zinc? Because zinc is more active than iron. So when it reacts with oxygen, it will form a very hard, unreactive layer of zinc oxide to prevent oxygen from reacting with iron. As you can see here, there's iron here, and I put zinc on top. Now zinc will react with oxygen and form zinc oxide. It will form a strong non-reactive layer which will prevent iron from reacting with oxygen. Okay, so these are the 5 barrier methods used to prevent rust. Stainless steel is an alloy of 3 metals, 72% iron, 18% nickel, and 10% chromium. Stainless steel is chemically inactive, inert. The last part of topic 4, electrochemistry, is going to be electroplating, something very simple and easy. It will just take 1 page and approximately a minute. Electroplating is by using electricity to plate metals to make it look more expensive and more beautiful. Process is very simple. You have an electrolytic cell, anode and cathode. You place the metal at the anode. The ions are going to move to migrate to the cathode, and the object is placed must be at the cathode. Okay, so the metal M will lose electrons and the ions in the solution, and it will lose an electron. These ions of the metal will then move to the cathode, okay, and they will become electroplated. Basically, the ring or spoon is going to gain the ions and become electrolyzed over here at the cathode, okay? So electroplating is something very simple, and that is it for all the episodes of topic 4 in electrochemistry of IGCSE chemistry 0620. Okay, I think I have divided it in approximately 8 episodes, and if you have any questions regarding any one of the topics, I'll be more than happy to help in the comments below. Other than that, I shall see you in the next one.